We have our next speaker. It's Olga Seleznova with a talk, Optimization of a Supply Chain by Applying Targeted Bayesian Network Learning to a Stock Allocation Model. Olga, are you here? Yeah.
Yeah, I hope you can see and hear me well.
Yeah, we see presentation.
Okay, perfect. And you can see me as well, right?
Yeah, we see well.
Perfect. Okay, so hi everybody. I am Olga, and today I will be talking about my research for master's research about optimization of a supply chain by applying targeted Bayesian network learning to a stock allocation model. This work was supervised by Dr. Aviv Gruber. I hope that he is here, and you may refer your questions to him as well. So let's start. The research aimed to optimize the stock allocation to improve supply chain management of an aviation system. The contribution of the work was done in twofold. First, we developed formulation of an extended stock allocation model. This model allows a local repair as an additional source of stock allocation along with the central depot support. And the second one, we propose structural insights of how to plan, manage, and operate a supply chain cycle in this specific ecosystem. And so today I will start with the explaining the meaning of supply chain management, stock allocation models, and ecosystem parameters for structural insights. Supply chain management. This is the integration of key business processes from end user through original suppliers that provide products, services, and information that add value for customers and other stakeholders. I hope you can see the laser. So from this picture, you may see that, yeah, this is from the user, end users through suppliers and until the customers. What about ecosystem? In this work, we are focusing on repairable systems, where the demand is driven by system failure in a deployed field. A system failure is always a result of a component or a part failure. So what happens? Upon a failure of a part, the system is repaired by replacement of a failed part by a ready-for-use spare part. We also may call it a replenishment system. The failed part is shipped to a repair facility, a depot, to undergo a repair process. Once the repaired component has become available, it is stockpiled at a central warehouse adjacent to the repair facility as an available part. Don't be afraid. I will visualize and show you all this cycle in detail later. But before that, I would like to underline that management of repairable spare parts for replenishment system is conducted on 3 levels: strategic, tactical, and operational. The strategic level addresses supply chain design tasks such as setting capacity levels and the graphical placement of facilities. At the tactical levels, policies and parameters within the supply chain infrastructure are established, as well as field stocking locations needs. We call it also FSLs in short. And operational planning focuses on a daily decision-making about choosing the optimal way to allocate available repair capacity, meaning relocating parts which require repairing among different items and available inventories to field stocking locations. These levels were presented by Caggiano, and we'll also discuss about another involvement of Caggiano in the research later. So in this work, we focus on specifically operational level of repairable service parts management, or in other words, on the daily decision making. Optimal inventory control is an important task in supply chain management. It aims to reduce the supply chain cost by controlling inventory in an effective manner. Supply chain. So here effective means that supply chain members will not be affected neither by surplus nor by shortage of inventory. Inventory meets an expected pattern of demand by maintaining a reasonable balance between cost holding the items in the inventory and the penalty of running out. Surplus versus shortage of inventory, inventory demand, cost of holding, and the penalty of running out. These underlined terms are used in the stock allocation model, and therefore let's review. Let's try to understand what stock allocation model means. So, as I have already presented, as I already said, stock allocation model was presented by Casciano et al. In 2006. This model concerns the operational planning or daily decision making, and the model consisted of a central repair part, central warehouse, and set of FSLs, which move from where spare parts are moved to the customers or repair queue. So the cyclic flow, so here is the cyclic flow of the SAM, stock allocation model. And it may be, this is very important, that this model considers inventory of each part type in various places in the system at any given point in time. So the spare part at any point in time may be in 7 states, as is shown on the figure. State number 1, here it is. State number 1 demonstrates the item in transit from an FSL or customer to the repair facility. State number 2, the item is awaiting repair at the repair facility. State number 3, the item is repaired at the repair facility. Number 4, it's in transit from the repair facility to the central warehouse. Number 5, the item is on hand at the central warehouse. Number 6, it's in transit from the central warehouse to FSLs. And finally, it is on hand at the field stock allocation FSA. For each part time, we must capture 3 types of parameters. The first one, the current stock level at the central warehouse, and quantities following arrival at the central warehouse over the planning horizon. How many parts and of what type we have in the warehouse. The current stock levels, the next one, the current stock levels at the FSLs and the quantities following arrival at these locations as the consequence of inventory allocation decisions. So what we decide and where are the items in the FSLs and how many. And finally, the very important one, the costs for each period as a consequence of the inventory allocation decisions. Now, the task here is definitely to optimize costs, decision parameters, demand, and everything we already discussed as a need for supply chain management. Another model by Caggiano et al. Is an extended stock allocation model. The extended stock allocation model deals with making allocation decisions for parts arriving to FSL faster than by regular shipment. In the ESAM, the decision maker has an option to choose whether to send items by the regular transportation or by expedited one, by the regular mode or by expedited one. In making allocation decisions, the benefit of expedited shipment must be weighted against the incremental cost. Does it make sense to pay more when we need items faster? The visibility of this decision maker and the length of planning horizon of the ESAM is the same as of the ESAM. I went quite quickly through the SAM and ESAM to present you the model SAM3 that was actually presented in the research itself. And why did we need it, the SAM3 model? So while SAM and ESAM addresses stock allocation of multiple FSLs with a simple central repair facility, it does not and cannot address extended considerations of local repair facility. There are two reasons for this. The first one, they define a single decision variable of how many spares to send in a short horizon from central warehouse down to the FSS from each type and each time unit. In order to address local repair facility, the model has to have an additional decision variable, which is not present in the SAM, stock allocation, the initial stock allocation model. Therefore, we need additional variable of the local facility to implement this local repair. And another one, adding local repair facility creates two levels of horizon, meaning two parameters, two time constraints. One to repair items locally, and another one to repair items by the regular type. As a result of these gaps, we proposed research. In the research, another model called SAM3. Before I go to SAM3, I would like, do we have any questions? No. Great. So, in the SAM3, the process of sending failed items from FSL to the central warehouse is borrowed from the stock allocation model previously presented. The SAM3 extends the SAM model by enabling the opportunity to send failed items to an expedited repair cycle at a higher cost, which actually means repairing the items locally. The role of ESAM is more as an inspiration of the expedited or in other words local repair cycle at a higher cost. So this is the basic structure of SAM3. We have the central depot, just as it was in stock allocation model SAM. We have two FSLs because the research is constrained to two echelon repair facility. And then we have post-inspection. In post-inspection, we make decision whether to repair locally. Meaning decision maker makes decision. If the answer is yes, so the item is repaired, takes back to FSL here 1 or 2 respectively, and repairs in the FSA. If the answer is no, item is sent back to the central depot and repaired by the regular cycle, just as it was in a stock allocation model. Again, the extension here is the existence of this post-inspection, the existence of post-inspection and the availability of local repair items. Okay, SAM3 requires to capture the following types of parameters for each part type, which are necessary to understand structural insights. There are 5 types: cost-related parameters, supply parameters, decision variables, time-related parameters, and features that were generated based on the previous 4 parameters. The first one, cost-related parameters. Here are actually here you see 4 parameters. The first 2 were present in the stock allocation model. Another 2 are in addition for SAM3. So HIJ, here you see it as HI1 because it is for FSL1, and I is the index for item type. So HIJ is an incremental cost per period associated with the holding a unit at FSL instead of at warehouse. Pi ij, pi I1, and pi I2 are units shortage cost per period for item at FSL. These parameters were borrowed again from the stock allocation. CIJ and ZIJ are specifically for SAM3 because they deal with the local repair. CIJ is the shipment cost of a component type I from the depot to FSL, and here it is. And Z is the incremental cost of repairing a component of type I at FSL instead of the depot. These cost-related parameters resulted into the features that these features were created to gather better insights. The first one, RCZ. This feature was created by the formula Cij divided Cij plus Czij. This feature expresses the ratio of shipment cost to the sum shipment and repairing the item at FSL. In other words, the feature helps to understand how costly it is to send items. Values of RCZ are distributed from 0 to 1, and they include the value called NA. You will see it in the network, and it means that Z and C are 0, or shipment cost is for free. RH-pi is the feature describing how costly it is surplus versus shortage in the storage of FSL. The formula for this is H divided H plus pi. Another feature compares the unit called cost relation. It compares the unit shortage cost pi to other cost-related parameters mentioned above. The goal of this feature is to indicate how costly is the FSL storage management compared to the logistic cost. There are 4 logistic values that are considered by the model. pi is the case when pi is less than c and z. The case when pi is greater or equal than c or z, pi is greater than c plus z, and the last one, pi is greater than c plus z plus pi, plus h, I'm sorry. Supply parameters. So S tilde I0 is the known cumulative supply items available at the central warehouse through period of time. You do not see this parameter on the figure because it is related to the stock allocation model. Instead of this, in SAM3, you may see the cumulative supply item available at warehouse through specific period, and it is affected by repair location decision. Here, this parameter, CI0, it is called. S tilde I1 and I2 are known cumulative supply of items available at the relevant FSLs through period of time. And S tilde F is the non-cumulative failed items at FSL through period of decision making. Decision variables. So here, YRI1 and YRI2 are numbers of units to ship by regular transport from the central warehouse to FSL in time period. XW, I1 and I2 are number of units to be sent to repair from the central depot to the central depot. And XB, I1 and 2 are numbers of units to be sent to each FSL. Based on decision variables, were created two more features that will be used in the as targets in TBNL. I will explain it a bit later. RXB, XW were created by the formula XB divided XB plus XW. And this feature considers the ratio between items to repair at the FSL and the number of items to repair totally at the FSL and at the warehouse. And the next one, YRXW, was created by the formula YR divided YR plus XW. This is the feature describing how many items are sent to FSLs out of all repaired items. For simplicity of structural conclusions, we chose to represent these two features in buckets of values, and the buckets of values are presented by their upper bound values. And the last one, time-related parameters that are, because they are time-related, are always non-negative, and they are modeled as integer numbers of time period. So the first one, TI0, this is the repair lead time for item, including transport to the central warehouse from the repair facility. TIB is the emission lead time until available for shipment. So the time that we need to make decisions. TIG per each TI1 and TI2, depending on the FSL. This is the variable for each FSL, meaning base repair lead time until this item is available at FSL. And TRI1 for FSL1 and TRI2 for FSL2 variables per FSL, of course, which is the repair transportation lead time for item I from warehouse or central depot to FSL. Now, to explain the SAM3 cycles, we need to so I need to explain the difference between the complete cycle and the sub-cycle to then explain the structure of insights. The sub-cycle means the process since the failed item is sent to repair until it is returned to the base. And a complete cycle includes the time since failure until a decision is made regarding this failed item. So depending on the values of time-related parameters, SAM3 model is split into 5 mutually exclusive and complementary cases. They were determined by the business knowledge about how often they occur in the industry and distributed as follows. Case 3 is the most numerous. It is called slow local repair, and it is 45%. Case 1, rapid local cycle, and case 2, rapid local repair, are 20% each. Case 4 is slow inspection, which is 5%, and case 5, immature local facility, is 10%. So depending on the case, these values were generated depending on the case, different amount of time. For generation, I will explain it a bit later in details. We used NumPy random generator. But first things first. So we have 5 cases, and now let me explain you the difference between all these 5. The very important thing is that they are mutually exclusive. So all the structure of the models is explained, or the parameter space is explained by one of these 5 cases. Case 1, rapid local cycle, means that the shipment time from the depot to the base takes more time than a complete local cycle, as presented in the timeline. TIJ plus TIB is less or equal than TRIJ. Case 2, rapid local repair, means that the shipment time from the depot to the base takes more time than a local repair, but it is shorter than a local cycle as shown in the timeline. TIJ, so you can see the timeline, and the expression used for generating each of the cases is case 2 is TIJ is less or equal than TRIJ and less than TIJ plus TIB. Case 3, slow local repair, means that the shipment time from the depot to the base is shorter than a local repair. But a local repair does not take more time than a sub-cycle. Remember, I explained by this sub-cycle that we mean by this the processing the failed item is sent to repair until it is returned to the base. Case number 4, called slow inspection. This means that the repair time at the base takes more time than a sub-cycle via the depot, but no more than a complete cycle via the depot. Since TIB, the decision time, is assumed to be relatively short, the cycle difference is always close to case 5, defined below. Case 5 Immature local facility means that the local repair takes more time than a complete cycle via the depot. It is anticipated that only if shipment cost is considerably high or if the incremental cost of a local repair is negative, then a local repair will be favored. And the expression is Tij is more than Tr plus Ti0 plus Tiv. According to the cases formulation, we extracted structural insights. But before we go to the structural insights, let me show you the SAM3. How does it look like? So the model is written in Python. It is basically a Python class that inherits SAM class parameters. The input for this class is generated by the NumPy randomizer given the pre-specified parameter space, meaning the set of values that might appear. For example, T0 might be from 3 to 15. So for each case, the pre-specified value is chosen by the NumPy randomizer. And the model includes optimization functions and constraints that generate the following values. So these values in green were generated as an input to the SAM3 Python class. Based on these values, we generate features. These features are used to yield insights about relations between parameters, and they represent the relevant structural conclusions. So the, for example, the dependency between C and Z, pi and h, and so on. And finally, the model outputs decision variables that we already discussed using CVXPy optimization engine. Here it is presented as a sum, XB sum, but originally this is the matrix. Each cell of the matrix is the time horizon parameter. And the sum and the final features are used as a target in the TBNL algorithm. So by final features, I mean Rx, Bx that you already saw in the as a feature. And here are its values. Now here comes machine learning, and TBNL is a targeted Bayesian classifier which aims to maximize the conditional mutual information about a predetermined target variable. Generally speaking, Bayesian network is a network which has a descriptive interface, which is very useful for our task to yield insights from these rate table data, which would be not very easy to do manually. And actually that is the reason for using machine learning classifier. TBNL differs from other targeted Bayesian network classifiers by the fact that it proposes the upside down paradigm. It is placing the target variable as a sink to the network and 6 explanatory variables within the domain. These explanatory variables we may call as parents. We call it as parents of the target variables. But as you remember, I talked about target variables in plural. So not only a RXY XW, but RXB XW are target variables. How it happens? Variables, so we use variables presented in the previous section, time-related, cost-related, and others, as an input to TBNL algorithm. The output of this algorithm has TBNL structure. This consists of a predetermined target variable, which serves as a tool for structural conclusions about SAM3 model. For each case, we suggest an explicit TBNL structure, which I will present later. The target variable for TBNL is the RYXW, and recall that it describes how many items are sent to FSS out of all repaired items. However, I already mentioned that SAM3 extends SAM and ESAM models, allowing for local repair. Local repair, XB, is a very important variable to explain the structure of the model. So we wish to see this in the network. The problem is that TBNL accepts only a single target variable. And since we wish to see this variable, we call it by target variable. RYXW and RXBXW, we call it as by target variable, and they are connected by joint probability distribution of these two. And to see the second variable, the second semi-target variable XBXW in the network, we manually forced it to be one of the parents, explaining the main target one. Okay, so how do we create TBNL structure? The input data for each TBNL model is a subset of data with a predetermined case. The algorithm first selects the variable with the maximum mutual information between target and target variable as the parent of the target. Then it adds the second parent with the maximum information gain that is the mutual information about the target variable given the first parent. Then it does the same for third parent and so on and so forth. In our case, only 3 parents were allowed for the network, and the fourth one, the semi-target, was added manually. The whole process, so this we end up with the TBNL nuclear structure. And next we apply again a TBNL learning process for each parent on the values that are not yet parents, so that we create the TBNL of TBNLs, which corresponds to the definition of the TBNL method, and hence it is the instance of the TBNL network. The idea behind this repeated procedure is to create 2-level descriptive model, which helps us explain as fully as possible the structural and yield the structural conclusions. How the training happens, I will explain before before I show the actual networks of as a result of the TBNL. Training the TBNL was done by sampling the space of all possible setups for each case of the 5 cases exclusively. 5 different TBNL models, each has a network structure and its particular parameters. TBNL models output includes policies for each case. Cases policy I already showed in the previous slides. Each policy is a result of a network structure interpretation, and by analyzing propagated conditional probability of a by-target variable by setting evidence. So how setting evidence happens, and here is the TBNL output structure. So here is case one. Case one, called rapid local cycle, has the main parent, the target RYRXW, and the manually added parent XBXW, supposedly, and it explains the target one. Apart from this, we have CIG, the cost parameter, the shipment cost, S0 tilde, items available at the warehouse, and TIB, in other words, which means the decision time. So some parameters have the hat sign. It means that this parameter was quantized just due to the computational reasons, and the ease and to help to extract insights. These values are 10, for example, 25, 35, and 45 are the upper bounds of the quantile values of this parameter. So each of the parents have their own parents. So the parent of TIB is TRI2, regular transportation lead time for FSL2. The parents of SI0 tilde are the semi-target variable RXBXW, and S tilde for FSL1. The parents for CIJ is RH pi for FSL1, which is the ratio of H and the kind of ratio of H and pi, cost, meaning how costly is surplus versus shortage in the storage of FSL1, and cost relation for FSL1. So how do we extract insights based on this structure? First of all, you may see the price distribution that will help us later. And second of all, for example, let's take a look at the first evidence. So CIJ equals 45. In case of CIJ equals 45, which will create this square, C equal 45 will be not 20%, but 100%. So our task is to understand what will change in case these values will be 100%. So, and SI2 for FSL, meaning for FSL2 equal 25, will be also 100%. So in this case, meaning if the shipment cost from the depot to the FSLs is expensive, and the stock acquisition is in FSL2 is fairly sufficient, then the best policy would be local repair and fairly high support from the depot. How we got to this policy, because you may see that for XBXW, in case these evidence are 100%, the value equals 1 will grows from 56% to 88%, which is quite meaningful. RYXW grows from 40 equal 1, grows from 43 to 76%, which is also again quite high growth. The previous policies is emphasized even more in case pi I for FSL2 is added. So if it is if the shortage cost of spares in FSL2 is high, so the policy is even stronger. All that I described just now means that we may use this policy to definitely make decisions using the TBNL targeted naive Bayes structure. For case 2, rapid local repair, we also have two policies. But before that, let's look at the structure of the network. Cases 1 and 2, as you may suppose from their names and their time constraints, are quite similar. And we may see this from the structure as well. I will get back for a second to show it again. So the structure is quite similar. The main difference is in the following: that TI0 is a parent of the target variable instead of TB. So in case 2, decision time that we need to make decision is less important than transportation lead time. And the policies are as follows. So if in case SI1 equal 15, so for FSL1, here it is. So if the stock acquisition in FSL1 is fairly low, and both shipment cost CIJ and shortage cost pi I2, shortage cost for FSL2 are also high, then the optimal policy is local repair and high support from the depot. What does it mean? XB grows from 21% to 56%, and RYXW from equal 1 from 24 to 52. Again, quite meaningful growth. The next policy is if the storage in the depot is relatively high, meaning CI0 is 25. Its values distribution is 5, 15, and 25, and 100. So it's pretty low, pretty high, sorry. And the shipment cost is very high. 45 is the maximum. The policy would be most probably local repair and increased support from the depot. Again, the policy is even stronger. Okay, for the sake of time, we'll immediately go to the case 4. And this case slow inspection, called slow inspection. You may see totally different here, totally different structure. So here cost relation come to the picture, are depicted in the as a direct parent of the target. So we understand that for this case, this variable is very important for decision making. Let's take a look at the policies. So this setup demonstrates the less support from the depot. CI2 equals just 5. This is the minimum value, and less tendency to a local repair given lack of spare parts and long decision time. Long decision time is TIB equal 4, which is again the maximum value, The last policy is that it requires more support from the central depot through though not more than the average as shown. We will not take a look at the case 5 because we have a few more important information to consider. Okay. So, and finally, structural insights, something that was what everything was done for. So actually we proved that TBNL structure may give meaningful insights based on the propositions. Therefore we created 3 propositions. The first one was taken from case 1, rapid local cycle, and we chose these 3 because they were the most interesting ones and the most explanatory ones. So if the shipment costs are expensive and the local storage offers fairly high spare parts availability, then the best policy would be a local repair, regardless of its cost. Yet, it still requires a fairly high support from the depot despite the high shipment cost and despite the fact that the local storage offers a fairly high spare parts availability. Proposition 2, taken from case 2, rapid local repair, means that if shipment cost is low and the central storage offers a relatively high spare parts availability, the policy is to opt for a global cycle with least support from the central depot. And the last one, taken from case 4, slow inspection, means that if the inspection time is long, and the spare parts holding is limited, the policy tends to opt for a global cycle. However, if the inspection time is shorter, then the policy requires more support from the central depot, though not more than the average. And to conclude, we extended SAM and ESAM models. Given a setup of time, cost, and supply parameters, an optimization of a by-target variable can be obtained by running an implementation of the SAM3 model. A machine learning approach via the TBNL is used to draw structural conclusions, which suggest a policy for every possible setup. And as for the propositions, the shipment cost is a major factor of whether or not to establish local repair facilities. And this insight is already the strategic one, which might help to make decision in the logistics.